Hi everyone, today we are going to discuss about phase rule. Before that, we should know the chemical reaction. The chemical reaction can be classified into two types. One is a irreversible reaction and another one is a reversible reaction. First of all, we'll discuss about what is irreversible reaction. Irreversible reaction means the reaction takes place in one direction or in the same direction. That is called irreversible reaction. For example, zinc, it react with sulfuric acid. Now we'll get zinc sulfate plus H2. Okay, wow. Here in this reaction, the reactant react. Now we'll get the product. That is zinc is a reactant and H2SO4 that is another reactant. These two reactants react. Now we'll get zinc sulfate plus H2O. This is an example for irreversible reaction. Our next one is a reversible reaction. Reversible reaction means the reaction takes place in both the direction. That is forward and then backward reaction takes place. For example, calcium carbonate, it undergo dissociation takes place. Now we'll get calcium oxide plus carbon dioxide. This is a reaction for reversible reaction. Here the reaction takes place in both the direction, that is forward direction and also in the backward direction. That is calcium carbonate, it undergo dissociation takes place. Now we'll get calcium oxide plus carbon dioxide. This is the example for reversible reaction. Then why do we discuss about phase rule here? In the case of here, and another thing in the reversible reaction, it's again be classified into two things. One is a homogeneous reversible reaction. Another one is a heterogeneous reversible reaction. First of all, we discuss about what is homogeneous reversible reaction. Homo means that is same. What is homogeneous reversible reaction mean? Here the reactant and the product are in the same phase. For example, nitrogen plus hydrogen, it gives ammonia. In this reaction, nitrogen, that is a gaseous state, and hydrogen is in the gaseous state, and ammonia, that is also in the gaseous state. In this reaction, all the reactant and then product are in the same phase. That is called homogeneous reversible reaction. Our next one is a heterogeneous reversible reaction. Hetero mean that is different. In this case, what is heterogeneous reversible reaction mean? In this reaction, all the reactant and product are in the different phases. For example, the same example, here also you take the same example, calcium carbonate, that is, this one is the best example for reversible reaction. And then this calcium carbonate undergo dissociation takes place. Now we'll get calcium oxide plus carbon dioxide. Here calcium carbonate, that is in the solid state, and calcium oxide, this is in the solid state, and then carbon dioxide, that is in the gaseous state. Okay, here the reactant and the product are in the different phase. That is called heterogeneous reversible reaction. Okay, up to this, are you clear? And next thing is then why do we discuss about phase rule? Phase rule, in the case of homogeneous reaction, it is studied by law of mass action. But in the case of heterogeneous reversible reaction, it is studied by phase rule. It is studied by phase rule. Because in the case of heterogeneous reversible reaction, the laws of mass action is not applicable because the phases are different. So the phase rule is only applicable for heterogeneous reversible reaction. Okay, next one. What is law of mass action? The law of mass action is applicable only for homogeneous reversible reaction. What does law of mass action mean? The total mass of the reactant equal to total mass of the product. Total mass of the product. Okay, this is called law of mass action. For example, here also we'll take the same example, nitrogen plus hydrogen, it gets ammonia. Here nitrogen, that is in the gaseous state, and then hydrogen, that is in the gaseous state, and ammonia, that is in the gaseous state. Now apply, this equation is an example for homogeneous reversible reaction. Now apply the law of mass action to this equation. Here, in the left hand side of the equation, the total mass of the left hand side of the equation is equal to total mass of the right hand side of the equation. Here nitrogen, the atomic weight for nitrogen, 1 nitrogen, that is equal to 14. Here 2 nitrogen, 14 into 2, that is equal to 28. In the same way, hydrogen, now balance this equation. Here 2 nitrogen, that is 2 ammonia, here 3 hydrogen. Appa, how many hydrogen are present here? 6 hydrogen, 6 into 1, that is equal to 6. Appa 28 plus 6, that is equal to 34. In the same way, here also you'll calculate it, that is 2 into 1 nitrogen 14 plus 3 hydrogen that is equal to 3. Appa 2 into 17, that is equal to 34. Appa the total mass of the reactant side is equal to total mass of the product. Okay, this is known as law of mass action. Okay, and the next thing, the heterogeneous reversible reaction. So the phase rule is applicable. Phase rule is applicable only for heterogeneous reversible reaction. Okay, the phase rule was started in the year of 1874 by Billiard Gibbs. The phase rule, that is equal to, this is the phase rule, F is equal to C minus P plus 2, where F is a degree of freedom, that is denoted, a degree of freedom is denoted as capital F, degree of freedom, and then C is a number of components, and next one is a P is a number of phases present in the system, number of phase, and 2, that is the variable factors such as pressure, temperature, and then concentration. Okay, and next we'll discuss about what are the important terms involved in phase rule. And next we'll discuss about what are the important terms involved in phase rule. There are 3 terms involved in phase rule. One is equal to phase, that is denoted as P, and another one is equal to component, that is equal to C, and then third one is degree of freedom, that is denoted as capital F. Okay, now we'll discuss one by one. First one is a phase. I'll see the definition of phase. Phase is a homogeneous, physically distinct, mechanically separable portion of a system which is separated by definite boundaries from other portion of a system. That is, phase is equal to, phase is a homogeneous, and then physically distinct, and mechanically separable. Okay, now see the example. For example, the one component system, that is a water system. The water system consists of three phases. They are, that is, one is the ice, and then water, and next one is the water vapor. Ice, that is in the solid state, and water, that is in the liquid state, and water vapor, that is in the gaseous state. Okay, now compare these three things in the definition of phase. The first one is homogeneous. That is, the characteristics of ice, water, and water vapor are the same. And then second one is physically distinct. That is, the ice, water, and then water vapor can be physically distinct. And then third one is mechanically separable, means each one is having a definite boundaries. Okay, so now the system is consist of this is a water system. This water system is consist of three phases, that is P is equal to 3. Okay, up to this, are you clear? Okay, our next one, the phase, that is, they are classified into three types. One is a solid, another one is a liquid, and next one is a gas. In the solid, each solid is considered to be a single phase. The phase is equal to 1. And then in the liquid state, there are two things here. One is a miscible solution, and another one is a immiscible solution. Miscible solution, for example, here you'll take one example, that is sugar solution. The sugar solution, the number of phases, for example, sugar solution, the number of phases in sugar solution, that is equal to 1, because in the sugar solution, the sugar and water is completely miscible. Our next one is a immiscible solution. The second thing in the liquid, immiscible solution, here we will take one example, that is oil in water. Here, how many phases means, that is 2 phases. The phase is equal to, here, 2 phases. In the immiscible solution, the phase is equal to 2. For example, oil in water. Okay, our next one is a gas, and gas, they are completely miscible. There is no boundary between one gas to another gas. So, gas phase is considered as a single phase. Here, the phase is equal to, in the gas, the phase is equal to 1. Up to this, are you clear? Okay. Our next thing, next second term involved in phase rule, that is equal to component. Component. Now see the definition of component. Component is defined as a smallest number of independently variable constituents by means of which the composition of each phase can be expressed in the terms of chemical equation. What is component? What is the definition of component mean? Component is defined as a smallest number of independently variable constituents by means of which the composition of each phase can be expressed in terms of chemical equation. Now we'll see one example. Here also you'll take the same example, that is ice, water. Same example, water system. This water system consists of three phases. One is the ice, another one is the water, another one is a water vapor. Okay, the first thing, the ice can be expressed by the chemical formula, that is H2O, and water can be expressed by the chemical formula H2O, and then water vapor can be expressed by the chemical formula H2O. All the three phases can be expressed by the single formula, that is H2O. So the number of component is equal to 1. Okay, the component may be one component, and next one is a two component system. One component system is an example, best example for water system. The water system, it consists of how many components present in the water system mean C is equal to 1. In the same way, another one is a two component system. Two component system, that is copper sulfate pentahydrate 5H2O is a reversible reaction. This dissociate to get copper sulfate trihydrate plus H2O. The components in this reaction, from the chemical reaction, you are going to calculate the components from the right hand side of the equation only. Right hand side of the equation means the product side only. By using this product sign only, we are going to calculate the number of components. Here, in the right hand side of this, in this equation, how many components are present? There are two components. One is a copper sulfate trihydrate, another one is a water. How many components present in this equation mean component is equal to 2. This is an example, best example for two component system. Okay, up to this, are you clear? Our next one is a degree of freedom. Now see the definition for degree of freedom. Minimum number of independently variable factors that must be fixed to define the system completely. This is the definition for degree of freedom. That is, any one of the, that is variable factors, that is pressure, temperature and concentration. Any one of the variable factors must be fixed in order to define the system completely, and then also used to calculate the degree of freedom. Here also you will take the same example. For example, ice, water and then water vapor. By using this equation, by using the system, now you are going to calculate the degree of freedom by using the phase rule. What is phase rule? F is equal to C minus P plus 2. F is the degree of freedom and C is a component and P is the number of phases present in the system and 2 is a variable factor such as pressure and temperature. For example, here F is equal to, here you will take the same example. In this system, how many components present in the system mean, that is C is equal to 1. And then P is equal to how many phases? There are 3 phases. One is a solid, another one is a liquid, another one is a gas. 3 phases. Now apply these things in this phase rule. Now we'll get F is equal to 1 minus 3 plus 2. Now we'll get F is equal to 0. The degree of freedom is equal to 0 or 0 variant or non-variant. The degree of freedom may be 0, 1 and then 2. 0, that is called 0 variant or non-variant. The degree of freedom is equal to 1 mean that is univariant. And then another one, a degree of freedom is equal to 2 mean that is called bivariant. Okay, that's all. Our next one is next we'll discuss about phase diagram for one component system. one component system. What does phase diagram mean? If any two degrees of freedom is plotted against each other, it is called phase diagram. For one component system, it is plotted between, for one component system, it is plotted between pressure versus temperature. Okay, ba? Okay. Now see the diagram for one component system. The best example for one component system, that is water system. The water system is consists of three phases: ice, water, and then water vapor. Okay, now we'll discuss about the phase diagram for one component system. This phase diagram contains three things. One is a curve, and then next one is a triple point or point O, and then next one is a areas, and the last one is a metastable equilibrium. Okay, now we'll discuss one by one. First one is a curve. This phase diagram, it consists of three curves. One is a OA curve, another one is a OB curve, and another one is a OC curve. There are three curves here in this phase diagram. One is OA, another one is OB, and next one is a OC curve. Okay, now discuss one by one. First one is a curve OA. Curve OA, this curve OA is called as vaporization curve. Vaporization curve. And next one, along the OA curve, what are in the equilibrium mean? That is liquid water and water vapor are in equilibrium. This is a liquid state and this one is a gaseous state. And then at point A, the pressure is equal to critical pressure that is equal to 218 atmospheric pressure. And then at point A, the temperature is equal to critical temperature that is equal to 374 degree Celsius. And then at beyond point A, only the vapor phase exists. Vapor phase exists. Okay, and the next thing, by using this equation, next we are going to calculate the degree of freedom. F is equal to, what is the formula? F is equal to C minus P plus 2. Here, along the OA curve, how many phases mean? There are two phases. One is a water, another one is a gas. There are two phases. And then C is equal to, already we said that this is a one component system, that is equal to C is equal to 1. Now apply all these things in this equation. You are going to calculate the degree of freedom, that is 1 minus 2 plus 2, that is equal to F is equal to 1. That is univariant. In the same way, on another curve, the second curve, OB curve, the OB curve that is also called as sublimation curve. And the next thing, along the OB curve, there are two things in the equilibrium. One is a solid ice and then water vapor are in equilibrium. Water vapor are in equilibrium. And then that is this one is in the solid state and this one is a gaseous state. Now by using this equilibrium equation, now we are going to find out the number of phases. How many phases? There are two phases. One is a solid, another one is a gas. There are two phases. And then C is equal to 1. Now by using these things, next we are going to find out the degree of freedom. F is equal to C minus P plus 2, that is equal to 1 minus 2 plus 2, that is F is equal to 1. Appa, the curve OA, the degree of freedom along the curve OA, that is equal to univariant. And then next one is a curve OC. This one is curve OC. This curve is also called as melting curve. Along the OC curve, there are two things in our equilibrium. One is a solid ice and then liquid water are in equilibrium. Solid ice and then liquid water are in equilibrium. And then this curve, this OC curve is slightly inclined towards a pressure axis. This shows that the temperature increases with the temperature decreases with increase in pressure. OC curve is slightly inclined towards pressure axis. This shows that temperature decreases with increase in pressure. And next one, now by using this equation, equilibrium equation, you are going to calculate the number of phases. P is equal to 2 and then C is equal to 1 and F is equal to C minus P plus 2, that is 1 minus 2 plus 2, that is F is equal to 1. Along the OC curve, the degree of freedom is equal to univariant or degree of freedom is equal to 1. Okay, and next one is the next thing in the phase diagram, that is called triple point or point O. This is a triple point. This one is a triple point or point O. At point O, the three curves meeting point, that is called point O or triple point. Okay, at triple point, the three phases are in equilibrium: ice, and then water, and then water vapor are in equilibrium. Okay, well, that is ice in the solid state and water that is in the liquid state and water vapor that is in the gaseous state. Now, by using this equation, you are going to find out the number of phases present at point O, that is P is equal to 3 and C is equal to 1 and F is equal to C minus P plus 2. Now, substitute these values in this equation, 1 minus 3 plus 2 and then F is equal to 0. But the degree of freedom at point O, that is equal to 0 or non-variant or 0 variant. Okay. And next thing is and the next one in the areas. There are 3 areas. One is AOB, another one is BOC, another one is COA. There are 3 areas, AOB and then BOC and COA. There are 3 areas. Okay, now I'll discuss one by one. First one is a area AOB, BOC and then COA. There are 3 areas. And then area AOB, in the area AOB only water vapor exists. And then area BOC only solid ice only exists. And then area COA only water, liquid water exists. Up in the area AOB only water vapor. Okay, by using these things, you are going to calculate the phase. Up how many phases present in that area? That is only one phase. That is only is a water vapor. It is in the gaseous state. And C is equal to 1 and F is equal to C minus P plus 2. Now substitute this value in this equation. 1 minus 1 plus 2 and F is equal to 2. At the area AOB, the degree of freedom is equal to bivariant or the degree of freedom is equal to 2. In the same way, the BOC area and then COA area. And then BOC area only solid ice. Solid ice exists. Here also you are going to find out the value of P. P is equal to 1. That is solid only exists. And then C is equal to 1 and F is equal to C minus P plus 2. 1 minus 1 plus 2 and F is equal to 2. Here also the degree of freedom is equal to 2 or bivariant. In the same way, COA. In the COA area, this is a COA area. At COA area only water exists. That is in the liquid form. By using these things, I am going to calculate the phase, number of phases. That is how many phases at COA area 1, C is equal to 1 and F is equal to C minus P plus 2. Okay, 1 minus 1 plus 2, F is equal to 2. The COA area, the degree of freedom is equal to 2. Okay, up to this, are you clear? Okay, and next thing, the last one in the phase diagram. The last one in the phase diagram, this one is a metastable curve. The OB dash, the dotted line curve, that is OB dash curve. This curve is known as OB dash curve. This curve is known as metastable curve or metastable equilibrium. Along the OB dash curve, there are 2 things are in equilibrium. One is supercooled water, and then water vapor. Supercooled water and then water vapor are in equilibrium. That is supercooled water, this one is a liquid state, and then water vapor are in equilibrium. What is supercooled water mean? The water is cooled below 0 degrees Celsius without the ice formation. That water is called supercooled water. By using this equilibrium equation, you are going to calculate the degree of freedom. F is equal to C minus P plus 2. Here C is equal to 1 and P is equal to how many phases? There are 2 phases. One is supercooled water, another one is a gas. That is 2 phases. And F is equal to 1 minus 2 plus 2. That is equal to F is equal to 1. அப்போ at the metastable equilibrium or a metastable curve, along this curve, f is equal to the degree of freedom is equal to univariant. Okay, that's all, ma. Thank you.